Let's start with the big picture here. The whole reason for collecting data is to look for patterns, relationships amongst variables. We're interested in these patterns so that we can then determine and create mathematical relationships or equations that we can attach to these, enabling us to make future predictions. Before we lend too much credence to the model that we create from this data, we must understand that taking data is inherently susceptible to error. Whether this measurement error come from the equipment being used or the person taking the data, there is variability in this data. We must understand that the line and its equation are an approximation of the data, and we need to develop a justification, a method for justifying that our line, our model, is a good representation of the data and that the model fits what nature is trying to show us. Justifying a linear model for a data set is almost like building a court case. There's a number of steps we have to go through and follow in order to make this justification. I'm going to review these here quickly, then we're going to go back through them individually. First and foremost, we look at the scatter plot of the data. If the pattern appears to be linear at the onset, we can then proceed. The next step would be to find the linear regression using some sort of technology to be shown in a later video, and then examine the R value. R represents the correlation coefficient that we discussed in previous videos. Here, we would then move on to creating a residual plot and looking then for a pattern. Looking for a pattern in the residual plot is a big step in justifying our model. Finally, we would use the R squared, or the coefficient of determination, to justify whether a linear model is appropriate or not for the data. All of these pieces of the puzzle have to come together and make sense, as we'll see here momentarily. In this slide, we see a scatter plot in which it's already been decided that a linear regression will be the best fit for the data. The linear regression line has been created, and I can tell you that the R value is very strong, 0.995. This by itself, however, does not necessarily mean that the linear regression is the best fit. This is one part of the puzzle as we put this justification together. Moving on in the process, we'll need to take a look at the residual plot. Before we look at the residual plot, let's discuss what a residual actually is. Let's begin by introducing the residual plots here. I'm going to create a scatter plot, just randomly picking some points here to create a scatter plot of looking at them, and they generally seem to follow a linear path. Here I'm going to number them. I know it's hard to see, but I'm numbering these 1 through 6 just to give the data points something, a reference, so that we can talk about them. I'm going to apply a rough best fit line, what I think is the best fit line of this particular data set that I've created. I'm going to now look at point number 2, and I'm going to draw a line between it and the line, a vertical line. This vertical line, let's call it delta y, is a residual. That distance between the y and the line is a residual. The point itself we've named y2. There's an imaginary point on the line that corresponds to the same x value that I'll call y hat 2. Well, y hat is then the predicted value. It's the value that the equation of the line predicts. My best fit line, I would probably write as y hat, the predicted y value, equals a plus bx. This is the equation of a linear relationship where the y hat is the predicted value. Each of these data points, every data point that we have here, has a predicted value and therefore has a residual. Some of the residuals will be bigger than others, but data point 1, 3, 4 has a tiny residual. Notice also that these residuals, some of them are above the x-axis or the linear regression, and some of them are below. To find a residual then, I take y minus y hat. This gives me sometimes positive values, sometimes negative values, whether I'm above or below. A value that's above the linear regression is going to give me a positive residual. Something that's below, here, like number 2 is going to give me a negative residual. So I will continue then on in plotting these points. Here, point number 3, which actually comes a little bit ahead of number 2. Point number 3 shows a positive residual, as it is above. Point number 4 is just ever so slightly below my least squares regression line, so it shows up very, very close to 0. The next point is above, the next one is below. I'm looking for a pattern here. I'm not seeing one in this particular data set. The residuals here are not showing me a pattern. That's a good thing. If there'd been a pattern here, it would shed doubt on the linear regression being the appropriate model. I'm going to create 3 other residual plots here, just making these up for effect. Here we see a pattern, a clear pattern in this residual plot, a shape of a curve. In the next set, let me create another pattern that sometimes occurs. Notice that the data points are showing up, well, close, and then as I move out on the x-axis, I'm getting some data points now, residuals, that are moving further and further away. It would appear as though the linear regression did a good job of modeling the data that had low x values. It's doing a poor job of modeling the data at these higher x values. Last, let's just look at a residual plot here. It would seem as though these points are coming in, some above, some below, somewhat random. This is a good thing. We do not want to see a pattern in our residual plot. The first residual plot, well, this first residual plot shows a pattern and probably excludes us from using it as linear regression as our model. But the third one, yeah, this one's a good model. Let's take a look here at the original least squares regression and its corresponding residual plot now. Notice that it shows a little bit of the horn effect, but not much. Those last few data points bring it back into a tame relationship. And I'm going to say that the residual plot here does show that there is no pattern and they are randomly placed. Notice at the bottom of this, they give you this value of r squared. And let's talk about that a little bit, the value of r squared and what that means. R squared is that coefficient of determination. R squared is one of the harder concepts to wrap your mind around in AP statistics, but let's give it a shot. Remember, an important concept in statistics is the idea of variation and how the data varies. Here it comes again. R squared is decided as the percentage of variation in the dependent variable that can be explained by the variation in the independent variable. Okay, I told you this was tough, but let's see what we can do with it. Basically what I'm saying is that the variation in my y data can be explained by the variation in my x data. Remember, taking data is inherently susceptible to error. If the error in the y data can be explained by the error that's in my x data, then I've got a very high r square value. We're going to discuss this more in class and do some examples. When you report a regression, give r squared as a measure of how successful the regression was in explaining the response variable. And r squared of 1 says that the variation in one variable is completely accounted for by the linear relationship with the other variable. More to come on r squared and linear regression as time goes by here, but for now we're going to sign this one off and do some exercises in class with this information next class meeting.